Hello, today we're going to go over some practice questions that use the Hardy-Weinberg equation. And if you find this video to be helpful, please subscribe to my channel, and that way YouTube will be more likely to recommend this video to those other people who are looking for help on the Hardy-Weinberg equation. Now, the first thing to keep in mind is we have two important equations that are necessary to really understand what we're talking about when we talk about the Hardy-Weinberg theorem. The first equation is P plus Q equals 1. And when we talk about P plus Q, we're talking about the frequency of the alleles. So P is the frequency of the dominant allele, and Q is the frequency of the recessive allele. The second equation we need to know is P squared plus 2PQ plus Q squared equals 1. And in that case, we're talking about the genotype frequency, okay? That is how the dominant allele P and the recessive allele Q, well, within a population, how can those come together to form an individual, right? To form a genotype. So we can have P squared, that's PP, two of the dominant alleles. So P squared is the homozygous dominant genotype frequency. We have heterozygotes that have one P allele and one Q allele. So those are the heterozygous genotype frequency. And we have the homozygous recessive genotype frequency. That's going to be Q squared, right? Those are the individuals with two recessive alleles. So P squared plus 2PQ plus Q squared equals 1. When we use this equation, we're talking about the genotypes. That is how the alleles can come together within the population. Now, if this all sounds a little confusing to you, check out my other video on the Hardy-Weinberg principle that breaks down P and Q and the allele frequency versus the genotype frequency. If you think you've got a good handle on the difference between alleles and genotypes and the two different equations here, well, let's continue on. So these are the two equations that we're going to use. P plus Q equals 1 and P squared plus 2PQ plus Q squared equals 1. Now, when we're working with both of these, it's the same P, okay? So if P over on the left equation is 0.5, well, then in the right equation, P squared is going to be 0.5 squared. Okay, so these two equations relate directly to each other. And in fact, the equation on the right is just the square of the equation on the left. Okay, P plus Q times P plus Q. That's what P squared plus 2PQ plus Q squared is. Now, I'm numbering the slides in the upper left-hand corner so that if you want to review how a certain part was made, you know which section of this problem we're working on. So here's our question, right? Here's our scenario. We're following a population of grasshoppers over 5 years, and we're looking at the allele for grasshopper color. There's two options, big T, which is the dominant allele, and little t, which is the recessive allele. Big T encodes tan color, little t encodes green grasshopper color. So the first thing we have to keep in mind is that the big T allele T, that encodes tan allele. Little t is the green recessive allele. We need to change this into the speak of Hardy-Weinberg. So big T, the dominant allele, is P. And little t, the recessive allele, is Q. So when we think about how big T and little t can come together within the population, well, if we have heterozygous individuals within the population, we know that we can end up with big T, big T. We can end up with two heterozygous options, right? Big T, little t, and big T, little t. And then 1 out of 4, or 25% of our options are going to be little t, or the homozygous recessive genotype. So a genotype of big T is going to lead to a phenotype of a grasshopper that is tan. The phenotype of a heterozygous grasshopper is going to be tan, because they have one dominant allele, tan, that overrides the recessive allele for green. And so little t, those are the homozygous recessive individuals, and they only have recessive alleles, so they are going to be the green grasshoppers. Now let's go ahead and translate these genotypes into the Hardy-Weinberg principle. Big T, well, if big T is P, remember we're using P and Q as variables, just like you would use X and Y, but P is the dominant allele. So big T, the dominant genotype is going to be P squared. Heterozygotes, which are big T, they're going to be 2PQ, and 2 because we have 2 of them, right? And then little t, the green grasshoppers, those are going to be QQ or Q squared. So when we look at that right equation, we know that p squared plus 2pq plus q squared equals 1, meaning that within our population, there are three options, really. There's homozygous dominant, p squared. There's heterozygotes, that's 2pq, and there's homozygous recessive, or q squared. And all those together, that's everything we have, that's 100%. So that all equals a frequency of 1. Now here's our question. We counted 1,000 grasshoppers at year 1 and 1,000 grasshoppers at year 5. Determine all allele and genotype variables. Has there been evolution in grasshopper color over the 5 years? So here are our numbers for year 1. We counted 500 tan grasshoppers and 500 green grasshoppers. At year 5, we counted 770 tan grasshoppers and 230 green grasshoppers. So at year 1, we counted 1,000 grasshoppers. Year 5, we counted 1,000 grasshoppers, and we looked at how many were tan or how many were green. Now, the question is, has there been evolution in grasshopper color over the 5 years? Looking at these numbers, well, there's certainly been a change. But our challenge is to use the Hardy-Weinberg principle to find the frequencies of the different alleles, P and Q. Because if those allele frequencies change from year 1 to year 5, then yes, there has been evolution in grasshopper color. So let's walk through and see how we would determine all of the allele and genotype variable frequencies. Now let's keep in mind that within the tan grasshoppers, we can have homozygous dominant individuals, big T, but within the tan grasshoppers, we can also have heterozygotes that have one dominant allele that's masking the recessive allele, okay? On the other hand, we know the green grasshoppers, because green is the recessive allele, green grasshoppers have to have 2 recessive alleles. They have to be little t, little t. Now, in the Hardy-Weinberg equation, p squared represents big T individuals. 2pq is the frequency of those heterozygous individuals, and q squared is the frequency of the recessive, homozygous recessive individuals. And when we're trying to figure out all of the different frequencies for p and q and the different genotypes, p squared, 2pq, and q squared, we always start with the homozygous recessive population, okay, little t, little t. We're going to start with the green grasshoppers because we know to be green, that grasshopper has to have 2 recessive alleles. If we start with the tan grasshoppers, we don't know if we're going to be looking at a tan grasshopper that's homozygous dominant, big T, or a heterozygous tan grasshopper that's big T, little t, okay, that's 2pq. So we start with the homozygous recessive grasshoppers, little t, which is q squared, because we know that those are all going to have 2 copies of the recessive allele. We can be assured of that, and that's why we start here. So we're going to start by figuring out the frequency of q squared. That's little t, those are the green grasshoppers. So we're talking about the frequency, the proportion of them. So we need to find q squared. How do we do that? Well, we start here. We know that the green grasshoppers are q squared. They are the homozygous recessive phenotype. So we can figure out the proportion of green grasshoppers compared to the whole. Now let's start with year 1, and then we'll move on to year 5. We have to do year 1 first, so we can figure out the allele and genotype frequencies for year 1, and then compare them to what we discover for the year 5 frequencies. So we're going to start with q squared. Q squared is simply the proportion of green grasshoppers because q squared is little t. So we have 500 green grasshoppers. There's a total of 1,000, so 500 divided by 1,000 is 0.5 or 50%, but we're going to leave it in frequency rather than in percentage. So the frequency of green grasshoppers is 0.5. Q squared equals 0.5. Now, if we have q squared, we can figure out q, right? So q is simply the square root of q squared. So q is the square root of 0.5. Q then is 0.71. So already we have figured out q squared, which is 0.5, and q, which is 0.71. So I've put those into the equation up top so we can see what we've already determined and which frequencies we have yet to determine. Now from this point, hey, we've got Q and we've got Q squared. We're doing great. We can figure out all of the other frequencies now because we know P plus Q equals 1. So if we have Q, we can figure out P, right? P plus Q equals 1. So 1 minus 0.71 is going to be equal to P. So P, therefore, is 0.29. I've gone ahead and filled in 0.29 up at our top equation, so we can see that we have figured out P and we have figured out Q. Now, if we have Q and P, that might be enough, depending upon the question. We figured out the frequencies of the P and Q alleles. But in our scenario, it says determine all allele and genotype variables. So we're going to determine the frequencies for the genotypes as well. And what we've got left is P squared. Those are the homozygous dominant individuals. And 2PQ. That's the frequency of the heterozygous individuals. But we have P and Q. So we can now easily figure out P squared and 2PQ, right? If P is 0.29, well, P squared is just 0.29 times 0.29. It's P squared. So P squared is 0.08. And similarly, 2PQ is just going to be 2 times P times Q. So 2 times 0.29 times 0.71. So 2PQ is 0.41. That's the frequency of the heterozygous population. Let's go ahead and fill that in now. Okay, so we have all of the allele and genotype frequencies now in this year 1 population of tan and green grasshoppers. Now, what does this mean, actually? We have these numbers. What does that mean? Well, remember that P represents the dominant allele and Q represents the recessive allele. So within our population of grasshoppers, there's 2 options, a big T or little t. And in this case, well, big T, that's P. So the frequency of the dominant allele is 0.29, or 29% of the alleles are the dominant allele. Q, on the other hand, is 0.71. So 71% of the alleles in this grasshopper population are the recessive allele. So when you're working with the Hardy-Weinberg equation, don't get lost in the frequencies, right? Just to remind yourself what P and Q stand for, or what P squared, 2PQ, and Q squared stand for. Now we looked at the alleles frequency. Let's look at the genotype frequency. So P squared, we know that number represents the frequency of the homozygous dominant individuals. So those are grasshoppers that are big T, big T. And here we see that that is 0.09, or 9% of the population is homozygous dominant. 2PQ, that number is 0.41. That's the frequency of heterozygotes in our population. Okay, so 41% of the population has 1 dominant and 1 recessive allele. And Q squared, that's the proportion of homozygous recessive individuals within our population. Green grasshoppers, right? And that's 0.5, or 50% of our population. So the Hardy-Weinberg principle is a few simple equations that allow us to figure out what the frequency of the alleles, P and Q, is, the dominant and recessive allele, and then the frequencies, therefore, of the genotypes formed by those dominant and or recessive alleles. So we have now figured out all of the frequencies for the individual alleles, P and Q, and the different genotypes that can result, P squared, 2PQ, and Q squared. This is how frequently these alleles or genotypes showed up at year 1 in the grasshopper population. We can't really see if evolution has occurred between year 1 and year 5, though, until we figure out the same variables for year 5. So that's your turn, okay? I want you to go ahead and figure out P, Q, P squared, 2PQ, and Q squared for the year 5 population. In essence, walk through the same process that we did here between slides 1 and 7 and see if you can use the year 7 numbers here, where there's 770 tan grasshoppers and 230 green grasshoppers, to figure out what the allele and genotype frequencies are at year 5. Now, I'm going to give you a few hints, and maybe you want to take a couple screenshots to help you walk you through it, but then pause the video See if you can figure these out, and then I'll reveal the answers when we come back. Now, the first hint I have for you is to start here, right? We know that green grasshoppers, those are little t. That's the homozygous recessive phenotype. That is Q squared. So if you can figure out the proportion of green grasshoppers at year 5, well, you've got Q squared. And from Q squared, you can go on to find Q, P, and then P squared and 2PQ. So remember, in our prior example, Q squared was 500 grasshoppers divided by the total number of grasshoppers. That's 0.5, right? 50% of our grasshoppers at year 1 were green. So Q squared is 0.5. So you'll do the same thing with the year 5 numbers using the number of green grasshoppers compared to the total population. Now, here's one thing to keep in mind. When we're looking at green grasshoppers, we know we're talking about a genotype behind that phenotype. That means that there's 2 alleles there, right? Little t coming together. So that is Q squared. That's not Q, because Q is just one little t. Q squared is the 2 t's together. That's the genotype, okay? So Q squared equals 0.5 in our previous example, not Q equals 0.5. This is the second list of hints that I want to give you. You may want to take a screenshot of this or write it down so that you can use these to walk through the process of finding all of the variables on your own. Okay, this is essentially the short list of how you go through and find PQ, P squared, 2PQ, and Q squared. Okay, take a screenshot of this, or if you want this more in prose rather than in short statements, then you can take a screenshot of this. This is more explanation written out in sentences, but it's the same as the slides before. So if you get stuck figuring out all the allele and genotype frequencies for the year 5 individuals, maybe come back to this information, see where you got stuck and what advice there is for the next step. So go ahead, figure out all of the allele and genotype frequencies for the year 5 individuals, and then come back to the video to see if you did them correctly. Okay, so hopefully you have figured out all of the frequencies for the alleles and genotypes for the year 5 numbers that we provided for tan and green grasshoppers. I told you we're going to start with Q squared. Q squared is the homozygous recessive individuals. We know that the homozygous recessive grasshoppers are green, so the proportion of green grasshoppers at year 5 is simply 230 divided by 1,000. So Q squared equals 0.23. Once we have Q squared, we can take the square root of that to find Q. So the square root of 0.23 is 0.48. Well, now that we have Q, we can figure out P because P plus Q equals 1. So P, therefore, is 0.52. We have P and we have Q, so now we can figure out the frequencies that remain, P squared and 2PQ. P squared, therefore, is going to be 0.52 times 0.52. That equals 0.27. And 2PQ is 2 times 0.52 times 0.48, and that equals 0.5. Let's fill all these values in so we can do a reality check. P plus Q, we got 0.52 and 0.48. And together, does that equal 1? It has to equal 1, or we did our math wrong along the way. So double check that it equals 1. And in this case, yes, it does. Again, what does it mean? Well, it means that P, that's the dominant allele that encodes tan, and Q, that's the recessive allele that encodes green. 52% of the alleles in this grasshopper population at year 5 were the dominant allele, and 48% of the alleles in this grasshopper population at year 5 were the recessive allele. When we look at P squared plus 2PQ plus Q squared, again, we want to fill in our numbers and make sure that it equals 1. And in this case, yes, it does. So it looks like we did our math correctly. What are we looking at? Well, remember, P squared is the frequency of the homozygous dominance genotype. So that's 0.27, or 27% of our grasshopper population is big T, big T. 2PQ, that number is the proportion of heterozygote grasshoppers at year 5. That's 0.5, or 50%. And Q squared is the proportion of homozygous recessive grasshoppers at year 5, or 0.23. That's 23% of the population. And to really answer the question, has there been evolution in grasshopper color over the years, we have to compare our frequencies from year 1 to year 5. And what do we find? Well, let's just look at the frequency of the dominant allele, P. Well, year 1, the frequency was 0.29. In year 5, it's 0.52. So over the past 5 years, there's more of the dominant allele big T than there was at year 1. Similarly, if there's more of the dominant allele, that means there has to be fewer of the recessive allele Q. And we see that as well. Now we can double check ourselves and take a look at the frequency of the homozygous dominant, heterozygous, and homozygous recessive individuals within our grasshopper population. And we see that those have changed as well from year 1 to year 5. So the answer is yes, there has been evolution in grasshopper color over the last 5 years. When we took our numbers then and we counted our numbers at year 5, we could have seen there's no difference in the frequency of the alleles. And if there's no difference in the frequency of the alleles, then that means that evolution didn't occur, that the population is being maintained at allele frequency then and now the same, similarly. But we saw actually that there's a difference between year 1 and year 5 when we look at the allele or genotype frequencies. So there has been some pressure on that population such that the dominant allele has increased and the recessive allele, now there's fewer recessive alleles than what there was. And there are several different reasons that might have happened. For instance, natural selection. What if the dominant allele, which allows for a tan grasshopper, what if those with a dominant allele, those tan grasshoppers blended in or camouflaged better in the environments in which they live? Maybe the green ones were more easily seen by predators, and so more of the green ones were eaten, leaving those that were tan to be able to breed and reproduce at a higher rate than those with the recessive phenotype. Okay, that's one example, but there are several examples of how evolution could occur. Now, I want to ask one final question, and that's because on an exam or in practice, you may see this question. We figured out all of the allele and genotype frequencies. Now the question asks, okay, well, what is the number of homozygous tan grasshoppers in year 5? Number, instead of frequency now, we're looking at number. We know that at year 5, there are 770 tan grasshoppers, but we also know within that 770, there are some that are homozygous dominant, big T, and there are some that are heterozygous, big T, little t. And this question is asking for, of that 770, what's the number of homozygous big T grasshoppers at year 5? Now, to figure that out, you simply multiply the total population for that year by the frequency that you determined. We want to know the homozygous dominant genotype individuals, so we use the frequency for P squared. P squared is equal to 0.27. So we multiply the total by 0.27, okay? 0.27 times 1,000, that's our total population for year 5, is 270. So 270 of those tan grasshoppers have the homozygous dominant genotype. Now, one thing I want to point out is that you multiply the frequency that you found by the total number, okay? So there were 1,000 grasshoppers at year 5, so you have to multiply 0.27 by 1,000. You do not multiply it by 770, okay? 770 shows you the proportion of tan grasshoppers. But remember, when we figured out P squared, 2PQ, and Q squared, well, we figured them all out to equal 1, or the total of the population. So when we figured out 0.27, it relates to the proportion of 1,000 grasshoppers, not just the proportion of the tan ones. And why I mention this is because I've made this mistake. I've seen lots of students make this mistake. It's a mistake you may make as well, but try to check yourself. When we use the genotype frequency 0.27, 0.5, or 0.23, we're going to multiply that number by the total population to figure out the number of the grasshoppers that we're looking for, the actual number rather than the frequency. If this question had asked for the number of heterozygotes in our year 5 grasshoppers, well, we would simply take, heterozygotes, that's 2pq. We figured out 2pq equals 0.5, so we would multiply 1,000 by 0.5, and we would find that there are 500 heterozygous tan grasshoppers in our population. So once you get the hang of working with the Hardy-Weinberg equations, this will become much easier, and innately you'll understand how to find all of the different variables here. Just remember that P and Q, we're talking about the alleles. That's the dominant allele or the recessive allele. P squared, 2pq, and Q squared, that's going to be the frequency of the genotypes. P squared is the homozygous dominant frequency. 2pq, that's going to be the frequency of the heterozygotes. And Q squared is going to be the frequency of the homozygous recessive genotype. And generally, if you're given numbers like this in a table, you always start with figuring out Q squared, because you know Q squared, that's little t, or the homozygous recessive genotype, whatever you happen to be working with. We can find Q squared simply dividing the number of the homozygous recessive individuals by the total, and that gives us the frequency of Q squared. From there, we can get Q, P, P squared, and 2pq, and we have all of the variables. Thanks for watching, and be sure to subscribe if this was helpful.